Hello. Hello. All right. Hey, everyone. All right. We have a few more minutes before we get started. All right. We'll wait 2 more minutes before we'll get started on today's lesson. All right. One more. All right. All right. So 1:31. Let's get started. So today's lesson. Okay. One more. Isaac coming in. So in our past 2 lessons, we have been talking about. We learned about how stars form, how they become main sequence stars, and then how those main sequence stars start to age. They turn to red giants, and they, depending on how big they are, they undergo like a supernova or a planetary nebula, right? And after those big explosions or nebulas happen, then what? What's left of the star? That's what we're going to study today. We're going to be studying white dwarfs. We're going to be looking at neutron stars, and our most interesting one most likely is going to be black holes. All right. All right, so let's get started. All right. So this is again our life cycle diagram, right? We already learned a lot about molecular clusters and open clusters, and now we're moving on, and we learned about everything in the main sequence, and how those stars start to age. And last time we touched just a bit on planetary nebulas and on supernovas. So let's dive into that. So first comes is the planetary nebula, right? Planetary nebula is what happens after all those outer layers of the star start to float away, right? Once a star reaches its red giant phase, all those outer layers, when there's no more fusion happening, right? These stars can't fuse carbon, can't fuse neon, can't fuse nitrogen. These heavier elements are just not big enough to fuse them. And as a result, there's less and less fusion happening inside the star. And without that energy source, the star begins to lose its grip on itself and it begins to expand like that. And so, as I said last time, a planetary nebula is it's a very slow process. It's not an explosion really. Things just start to drift away and drift away from the center, from the core. And so you can see a very clear layer here, right? So there are two distinct layers. This inside layer here is like our helium. That's helium burning, our helium burning shell, basically. And this is still hydrogen. So these are the two layers of like burning, basically. You can see similar things inside this nebula as well. Two distinct layers, which like if you imagine like if a star were to like just expand, then you would see these layers. Yeah, again, this is the helium layer, this is the hydrogen layer. And some nebulas are a bit more like asymmetrical like this, right? Where in these, there are two very distinct layers where it kind of looks like there's one circle and then another circle outside of it. This nebula has a really flat, wide shape and then another circle around it. And the reason for this is just not every star is the same. Sometimes stars, they're in the inside at their cores, they have really weird magnetic fields. They have really weird winds going on. They have really weird like storms inside the star. And as the star begins to lose its energy and lose its fusion, then whatever kind of chaos was going on inside the star beforehand, well, also gets carried out on this much larger scale as it begins to expand. So if we compare these two nebulas, we can tell a lot about the star. We can tell that this star was a lot more active than the other one because of how chaotic it is. You also see these strands, like these like pillars kind of coming out from the star. And that indicates that there's a really strong magnetic field at its poles. So if this is like the North Pole and this is like the South Pole, right? The star had a really strong magnetic field and kind of forced a lot of its matter and its gas out along its poles because of its super strong chaotic magnetic field. That's also what caused a really flat shape in the center, a really flattened shell. If you compared to this one, well, you also kind of see that magnetic like pillar kind of forcing out, and you can also see how the nebula is a bit flattened in this direction, right? It is a bit flattened. It's not a perfect circle, but it isn't as chaotic as this one is. If you look here at the Cat's Eye Nebula, it's even more interesting. The Cat's Eye Nebula came from a much, much bigger star. You see all these different layers, right? Like that. And all those layers come from the different shells inside the star. You have your hydrogen burning shell, helium burning shell, carbon burning shell, neon burning shell, etc. And so that's what all these shells are coming from. You can also tell that this star was a lot more chaotic and a lot more violent than the other nebulas we see here, because look at these shapes, right? Like they're flattened in one direction, flattened in another, a bunch of these ovals overlapping each other, creating this really interesting shape, right? Like that. And what that indicates to us is that, as I said, the star was really big because it has so many of these shells. It also was very chaotic because all these shells are jumbled up, right? They're overlapping each other everywhere. So by looking at nebulas, you can actually tell a lot about what happened in the star beforehand. Now, what about what's inside these nebulas? If we look at the very center, you see a little bright dot, right? What that is the core of the star. That's the core where all the deposit material that it couldn't burn, for example, carbon, nitrogen, neon, right? These are things that it's not big enough to burn anymore. So therefore, it all just sits in the very center of the star. That's what the core is. Here again, another core of that stuff that it can't burn. And it's the same in every single one of these nebulas, a really bright core in the center of stuff that the star can no longer burn. And what is that core? That core is our white dwarf, right? And we're going to discuss what a white dwarf is. So this is also a graph that we pulled up, an illustration we pulled up last time, which is kind of demonstrating what the life cycle of the sun is. We've studied how a star gets born from a protostar from molecular cloud. It enters its main sequence phase and doesn't really change at all, right? But the star does get gradually bigger and gets gradually a bit redder, right? Because the sun is running through its hydrogen. It's burning it up, and eventually it's going to start to run out of fuel. And as it does run out of fuel, that's when we become a red giant. When we start running out of fuel, the layers expand, the core contracts a little bit, and then we get our hydrogen burning shell, right? And then our core in the center, right? As we learned last time. And after the red giant runs out of fuel, once it stops burning helium and can't burn carbon, nitrogen, and anything heavier, then we have our nebula. So as it right here, planetary nebula occurs about right here. And then the very core, that center core that we saw in all those other pictures in the previous slide, that's our white dwarf. So we know that our white dwarf is made out of these heavier elements, made out of carbon, nitrogen, neon. I'll use white now. These are our heavier elements that form this. So let's learn a bit more about a white dwarf. So a white dwarf is governed by something we call electron degeneracy. So let's try to explain this concept. So we all know about atoms, right? We know that an atom has, well, a nucleus, and then has some electrons kind of orbiting around it, right? We've all seen drawings like this, right? This one might have 2 electrons. This one maybe has a lot more, something like this, right? But that's kind of what we think about when we think of an atom, right? And if you have 2 atoms, that's our core or nucleus of the atom. And here's another one over here. These 2 atoms can come pretty close to each other, right? Let's think about our water molecule. Like a water molecule is H2O. So H2O looks like this, right? You see this right here? That's a bond. That bond is basically how far apart these two atoms can be. That's what we call a very stable position for 2 atoms to be. Let's kind of zoom in on this, right? Let's kind of like if we zoom in on this bond here. If the hydrogen was too far away from the oxygen, then the two forces, they would kind of want to come together. They want to pull together because they're too far away from each other. They kind of get attracted to each other. If the hydrogen and oxygen atoms are too close to each other, they're actually repelled away from each other, because if it's too close, if you imagine it like, they imagine if they have like a radius around them, or like a boundary around them, which other atoms can't come close to. If an other atom comes too close to you, then it starts to repel itself away. Yes, Serena, do you have a question?
Is it like a magnet?
Yeah, you can kind of think of it at like a magnet. The real reason why they're repelled away from each other is not because of magnetism. It's something we call a strong force. It's like one of the we have four fundamental forces in our universe, which is the strong force, the weak force, magnetism, and gravity. So the strong force is what determines how far apart these atoms are allowed to be from each other. And so it's a very, and the reason why it's called a strong force is because it's very strong. And it's so strong that it can pull atoms together or push them apart. So basically, the hydrogen and the oxygen have to be this perfect distance away from each other. And that's the most stable. The strong force, well, they pull them together, but they also push them apart. And where that perfect equilibrium is, where they find that balance between the forces, that's what we call a bond. But sometimes what happens is, if you have so much mass, if you have so much mass like inside a massive star, right, inside the core of a star, where it's the densest part of a star, where it gets so hot it can even fuse elements, right? Fuse hydrogen, fuse helium. That's like 10 million degrees Celsius, right? It's very, very hot. When you reach that point, gravity actually overcomes the strong force. We focus on this right here. Let me just do this. With the focus on that force, right? As I was saying from before, if you have two atoms that are too close to each other, then the strong force tries to push them apart, because they can't be too close to each other, and they try to get away from each other. But if gravity is too strong, then you have the strong force trying to push out, but then gravity, this giant arrow, trying to push these two atoms together. And inside a white dwarf, that's what's going on. When gravity is so strong and it's so dense that it's overcoming the strong force and pushing these two atoms together. That's what we call the poly. Actually, we'll get to that in a second. But what happens is these atoms get pushed so close together that the atoms now look like this. Instead of being a perfect distance away from each other, they're now pushed together as close as they can possibly be. So if like these two, imagine if there used to be space between these two atoms, now those two atoms are just like that. They're just touching each other like that, basically. But why not go any further, right? So that's now we get to what we call the Pauli exclusion principle. And basically what this means is that these two atoms cannot become any closer, because even though gravity is a really strong force trying to push these two atoms even closer to each other, right? Because you have so much mass and so much gas trying to push all these atoms together, they get pushed back by the Pauli exclusion principle. And what the Pauli exclusion principle says is that these electrons here, like these, they cannot become any closer. They cannot overlap. If they overlap, then it violates this principle. And since these electrons really do not want to overlap, they don't want their orbits, these things called orbits, to overlap each other, that is what prevents gravity from pushing them together any further. And so this is what we call electron degeneracy. When atoms become so close and pushed together, they're basically touching each other, but they do not overlap. Do not overlap. There are no more bonds. There are no more bonds because gravity has forced them together. No more bonds. Atoms are all touching each other, but they don't overlap. That's what we call electron degeneracy. So this is what's going on inside a white dwarf, basically. White dwarfs are completely what we call electron degenerate, where all their atoms are forced together. And as long as that white dwarf is less than 1.44 solar masses, which means that this white dwarf cannot be heavier than 1.44 times our sun's mass, then our white dwarf is not going to collapse any further and just going to stay as a white dwarf for the rest of its life. If that white dwarf is bigger than 1.44 solar masses, then we might run into collapsing even further. You overcome the Pauli exclusion principle. You overcome that, and then what happens is these atoms will overlap each other. And these shells are going to overlap each other like that. But we'll get to that in a second, because that's what we call a neutron star. Yes, Rena?
What if it does violate the Pauli exclusion principle?
Yeah. Well, what I was saying is that any white dwarf that is bigger than 1.44 solar masses will violate the Pauli exclusion principle, because this force, which is pushing against gravity, making sure that these atoms do not overlap, that their shells don't overlap, that's what the Pauli exclusion principle is. And if you have so much mass, if you have, let's say, 2 solar masses worth of mass, then you will overcome it. And that's when you collapse even further. And that's what we call a neutron star. But we'll get to that in a second. We still have to finish up with white dwarfs first. So this limit right here, 1.44 solar masses, is what we call the I can't even say this, Chandrasekhar limit. Chandrasekhar limit. Chandrasekhar was this Indian dude who was just like studying nebulas, studying white dwarfs, and he realized that why can't we find any white dwarfs that are more than 1.44 solar masses? And then he realized, okay, that's because if they are even bigger than that, and they're going to violate this principle. And so that's what we call this limit. So all white dwarfs are electron degenerate. So here are some properties of a white dwarf. So a white dwarf, as I said before, is like the core of the sun, right? We know how big the sun is already, right? We know the sun is like, if it's massive, and the Earth is like this small compared to it, right? So if the Earth is about this big, then a white dwarf is even smaller than that, right? It's like this big. And that's what this graph over here is showing, right? That if you took the sun, and collapsed it down to a white dwarf, it would be even smaller than the Earth. The reason why they label this called Sirius B is because Sirius B used to be a sun-like star. It was a star about the same mass as the sun. It was a little bit bigger, but it was very close to the sun's mass. And long, long ago, it turned into a white dwarf. It underwent a planetary nebula, it shed its outer layers, and its inner core turned into a white dwarf. And so that's why we use it a lot as an example of a white dwarf, because Sirius B is very close to us, in fact. It's one of the closest white dwarfs to us, so that's why we like to study it a lot. So on Sirius B, which is a white dwarf, its gravity is almost 300 times as strong as the Earth's. its mass is over 300 times the Earth. So imagine everything on the Earth, all the matter, everything around you, right? All these different atoms. And if you collapse that, and no, not only that, it's 300 times what the Earth's mass is. So imagine 300,000 Earths, basically, and then shrink that down to something that's even smaller than the Earth. That's how dense this white dwarf is, where inside, let's say your fingers, right? You have a lot of bonds, you have a lot of atoms that are certain distances away from each other. Those bonds, or what the strong force creates, right? And if you smush that even further and get rid of all the space between all the atoms, that's how you achieve that white dwarf. So it's really crazy how much mass is inside a white dwarf. And as a result of being so much bigger than the Earth, that's why the gravity is over 100,000 times stronger than the Earth's. So if you were to stand on a white dwarf, well, you would just get instantly smushed. All your bones would just completely break if you try to stand on it, because it's so much stronger than the Earth's. The next thing that's really interesting about a white dwarf is that a white dwarf, after it sheds off all its layers in a planetary nebula, then you just have this really bright white dwarf, right? Look how bright it is. It's super white, right? Super, super white. And the reason for that is because it's still incredibly hot, right? This star was at 100, maybe 10 million degrees Celsius. So that's still a really, really hot temperature. And it's not immediately just going to become, really, really cold, right? It's going to take time for that energy to be radiated out. So as it continues to radiate energy, and as it does, it slowly becomes cooler and cooler and cooler, and it goes from a white color down to something a bit more red, something like that, right? But it takes a really, really long time for that to happen. In fact, a white dwarf actually has a lifetime even longer than the age of our universe. And we think the age of our universe is 13.7 billion years. And the lifetime of a white dwarf, we think, is even longer than that. So I think that's pretty insane. That white dwarfs that we see today are still going to be burning for billions and billions of years. Yeah. As I was saying from before, since this white dwarf is just the core of that red giant from before, they can't really fuse anymore, right? It's already lost so much mass. It's just this really dense core of carbon, nitrogen, and neon. There's no more burning. There's no internal fusion at all. So it's just slowly releasing its radiation away. Okay. So here are some examples of white dwarfs that we have seen. So here is what we call the M3 globular cluster. And so what a globular cluster is kind of just like a group of stars that all form together. And if we zoom in on that globular cluster, we see a bunch of these really faint white dots. I don't know if you can see that, right? This one's very clear. This one's really clear, but these really faint white dots. These white dots are all white dwarfs. And you can see all these stars around it, how they're really orange, right? They're really orange and really yellow. And that's what tells us these stars are mostly red giants. They're stars that are nearing the end of their life. They're about to, they're starting to burn out of all their hydrogen, and they start to become white dwarfs and undergo nebulas. That's why we see so many white dwarfs here, because all of these stars are basically starting to die out. Here is another look at our Sirius A. and Sirius B. So Sirius A is, well, Sirius B is part of what we call a binary star system. So if you look at it from above, here is Sirius A, and then you have another star, which is Sirius B, and orbiting around it. So these are two stars orbiting each other. That's what we call a binary star system. And so that's what this Sirius binary star system is. Sirius A is still a really bright blue star, but Sirius B is a really, really old white dwarf. So that's what we see in this picture here. And that's why Sirius B is so much smaller, because as you can imagine, a full-fledged main sequence star is a lot bigger than a white dwarf. But I think it's pretty cool that we actually have an image of Sirius B, of this white dwarf. In the picture here, this is an illustration. We don't actually know if this is the inside of a white dwarf, but this is what some people think a white dwarf could look like on the inside. On the inside, what they think is that this is solid. If you can imagine, when you have so much like mass clumped together like that, it becomes like a crystal, like a solid, because that's what solids are. When you have atoms so super, super close to each other, it becomes a crystal, it becomes solidified. So you have solid core, you have a liquid, like I guess, membrane, and then you have gas outside. So that's what scientists think happens to a white dwarf as it begins to cool down. Its core becomes more solidified. Its atmosphere, I guess, becomes more liquidy, and the gas membrane on the outside begins to turn to liquid. So like this is all carbon, nitrogen, and neon. That's all this stuff in here. Before we move on to there, I wanted to go to the white dwarf Wikipedia page. Because I thought that was a pretty cool image, or here. And this is what shows a white dwarf as it ages. It starts out this really, really bright white ball, and over time it begins to lose energy and begins to get redder and redder and redder as it becomes cooler and cooler and cooler. So why it stops at 13 billion years is because, well, that's the age of our universe. We don't know how much further a white dwarf can progress, but what we think would happen after, maybe 20 billion years or so, is that the white dwarf becomes so cold that we can no longer pick up any radiation off of it. Even all that red light just disappears, and we can no longer pick it up with our telescopes. At that point, that's what we call a black dwarf. A black dwarf, it's the opposite, obviously the opposite of a white dwarf, because it no longer is emitting light that we can detect it at least. Let's come here, right? So this is yet again our HR diagram. And so white dwarfs actually have a spot on the HR diagram, which is right here, right? And the reason it's there right here is because as they start out, they're really, really bright. They start out over here, right? They start out really, really bright, nice and hot, right? And over time, they begin to cool down. As they cool down, they become redder and redder and redder, and become more colder and colder, and become less brilliant, less hot. So that's why over time, they begin to slide down this diagonal here until they eventually just like disappear. Like that. Boom, gone off the graph. So those are white dwarfs. Does anyone have any questions? Anything? Serena, is your hand up from before, or is it a new question? All right. We'll move on then. So another thing that we touched on last class, well, we spent a long time on last class, was our supergiants. All right. And supergiants are super, super big stars, stars that have more than 8 times our sun's mass. And if they achieve that type of, if they achieve that much mass, then they can fuse heavier elements, right? The carbon, neon, oxygen, silicon, and whatever that normal low mass stars can't fuse, a super massive star can easily fuse it. So that's what forms all these different shells, right? These different silicon burning shells, oxygen burning cells, neon, carbon, hydrogen, helium, etc. And it keeps on burning all these different shells until it reaches iron. And once it reaches iron, iron is an incredibly stable element. The reason why we call it super stable is that it takes more energy to, like, the energy from, or energy created from iron fusion is less than energy needed to fuse iron. It actually takes more energy to fuse iron than the energy that you get out of it. So that's why you can't fuse iron, because it's super stable. You don't really get anything out from fusing it at all. And even if you did have the ability to fuse iron, you would just lose energy in the process. So as a result, that's why iron is the last thing that supergiants can't fuse. And here on the HR diagram, like, this is something that we also touched on last time, how every time it gains a new shell, it goes back and forth. It goes back and forth, back and forth, and that's that every time it goes back and forth once, it creates a new shell. But what happens after you reach iron? Once you reach iron, then that's the same thing as in a red giant, where in a red giant the layers start to fall apart, and you have and you start to have a nebula. In supergiants, you have something much more explosive. Yes, Serena?
How do we know that there are a lot of shells?
Oh yeah,
And
so
know what the shells contain?
yeah, so that was like something that we touched on last class. I think that actually might be a good time to review, because it was a lot. Let me see. Okay. So just as a quick review as how these shells even form, right? So main sequence stars, that's what they are. They have a core that's fusing hydrogen, right? So everything yellow is going to be hydrogen here, right? And slowly, as that hydrogen gets depleted, as you continue to burn it, you start to create helium deposits at the very center of your star, right? It's still burning completely fine, just that now you're starting to build up helium in its very, very, very core. And as you begin to run out of the helium, run out of hydrogen that you can burn, and you have more and more helium being deposited in your center, then what happens is the core collapses a little bit. The core collapses a little bit because it's starting to run out of hydrogen to burn. And as it collapses, the core gets even hotter. As it gets even hotter, then the hydrogen around the core, this hydrogen shell over here, is now able to burn hydrogen. It's not only the core that's burning something now, the outer shell has been created because the core got smaller, the hydrogen shell was formed, creating even more fusion, making the star even brighter and making the star even bigger. So that's the step between B and C. And as the hydrogen burning shell continues to fuse, eventually the core completely runs out of hydrogen. it's no longer fusing hydrogen, so therefore it collapses even further, making the star even bigger. But that also means that the core can now fuse helium. And this just continues to go over and over and over. Once the core runs out of helium to burn, it then continues to burn carbon, and it creates a carbon deposit in the center. And this process of collapsing the core, creating another shell, of burning hydrogen, helium, happens over and over. So this is a graph that we drew last time, which kind of demonstrates why our star kind of follows this really weird path along the HR diagram. As A, it's a main sequence star. It's just, it's sitting in place, not really changing. But what happens at B is that the star starts to run out of hydrogen, and therefore starts to burn helium. So the star gets just a little bit brighter and a little bit hotter. At C, that's when we start to create our hydrogen shell. At that hydrogen shell, we're transitioning and making the star even bigger. As the star gets bigger, its outer layers are even further away from the core. That's what makes them makes them cooler, right? Because the hotter you get, that's because you get closer and closer to the core. And at D, that's when we start to burn helium. And as we begin to burn helium, well, then we continue on this very stable path upwards. We're now just burning helium, and we're depositing carbon at the core of our star. So this kind of loop that happens is because a new shell has been formed. In this case, of this star, where the shell that we created was a hydrogen shell. But in much bigger stars, they create helium shells, they create carbon shells, neon shells. That's why massive stars have multiple of these loops. That's one loop, new shell created, another shell that's created, another shell like that. And the reason why this one seems so flat is because it's traveling back and forth so quickly that you can't really tell anymore. At 60 solar masses, you can see the same thing. It's just going back and forth so many times, and that's super quickly, that you can't really tell that a new shell is being formed by just looking at the graph. So that's why you have these different shells. And getting back on track, once we start to deposit iron at our core of our supergiant star, that's when we start to enter a supernova, right? This is also a process that we started to talk about last class, but now we're going to, again, go into more detail, right? So a supernova is created because you cannot fuse iron, right? So that's our iron core right there in the center. And if the core is no longer able to fuse, then gravity takes over, because that's really, really dense, right? Imagine like a really big ball of iron. And if there's no more fusion in the center, then gravity is the only force that takes over, right? Before in our core, we had equilibrium, right? We had fusion pushing outwards, gravity pushing in. And if we take away that fusion in the center, then the only thing that takes over is gravity. Gravity just forces the core to become even smaller. So gravity causes the core to collapse. And as that core collapses, see, it goes like this. All this black stuff here is what we call degenerate, right? The same thing inside a white dwarf. The core becomes degenerate, and all these atoms are squished together as close as they possibly can. But you still see these black arrows, right? These black arrows are even more mass. Even though the core has become degenerate now, you still have even more mass that's being collapsed in onto the core. So what happens is that in the supernova, the core overcomes the Chandrasekhar limit. And once it overcomes that limit, then our degenerate core becomes even smaller and even smaller, even smaller. That's where these red arrows come in. What the red arrows show is that once that core overcomes the Chandrasekhar limit, it basically becomes like a solid ball, right? It becomes a solid ball of just particles. You no longer have individual atoms or anything, you just have neutrons and these protons and electrons, just these very fundamental particles all squished together. And when you have that really solid ball, any other matter that hits that ball, you can imagine if another piece of matter hit it, it will just bounce away. Like a bouncy ball, basically. If another particle hits this ball, it will bounce off. Because that's just how dense that core has become. That's what the red arrows show. The red arrows show as more matter begins to hit this core, it generates a shock wave of stuff bouncing off of the core. And as that shock wave continues on, it goes bigger and bigger and bigger. As it gets bigger, that means you have even more space for matter to hit it, right? If you imagine a really small sphere, a really small sphere has a very small surface area, so therefore it can't really touch as much stuff. If that bouncy ball gets even bigger, then you have a much bigger surface area, even more stuff can bounce off the bouncy ball. So as the ball gets bigger and bigger and bigger, as the shock wave continues to expand, it only grows in speed because you have more mass hitting it. You have even more like energy for that shock wave. The shock wave gets bigger and bigger and bigger and stronger and stronger and stronger until the whole star just explodes. So these are all supernova remnants, that we call. A star underwent a supernova, and this is what remains of it. So let's kind of go through each of these, I guess. So here is one of our most famous nebulas, is what we call the Crab Nebula. Crab Nebula. So we call it a nebula, but it really is a supernova. Right, I don't know if you can tell, but if you see these lines here, I don't know if you see these circles, really faint circles. But what these circles are matter and gas, all orbiting around the center right here. That center is actually a neutron star. A neutron star, which is what happens, after you pass the Chandrasekhar limit, and all those atoms no longer are atoms anymore, and those atoms are broken apart, and it's just neutrons, protons, and electrons all squished together. So that's what's right there in the very, very center. And the rest of this, all this other stuff, all the really pretty oranges and greens and everything around it, that's what remains of the star. Those are the shells that we saw from before. Right? All these shells over here, all the hydrogen, helium, carbon, neon, oxygen, silicon, which are all different colors and all different at all different places in the star, right? Hydrogen being on the very outside and silicon being very close in. That's what causes the center of the star to look so much bluer and the outside to look so much redder, because of all these different shells being ejected away. But as you can see, you see these filaments, everywhere. It looks really, really chaotic what's going on here. It's not so symmetric like we saw in a planetary nebula, right? Because if you can imagine, the shock wave is really, really powerful. The shock wave is not slow. It happens very quickly. It happens in a matter of like seconds, literally in a matter of seconds. So that's what causes this supernova to look so chaotic, because it came from a very chaotic supernova. So that's the Crab Nebula. Here is another nebula. This doesn't have, some people call it the Hourglass Nebula, and you can kind of see why. Hourglass Nebula. And the reason for that is, well, because it kind of looks like an hourglass, right? You have the end here and end here, and it tapers towards the center. That's our hourglass. And this is another supernova. At the very center, you also have a neutron star there. But why does this nebula, this supernova, look so different from the Crab Nebula, right? You know, it's like, it looks so different. And the reason for that is because scientists believe that as the supergiant was beginning to was about to explode, it started spinning really, really, really quickly. And it started to spin. It gathered a lot of mass near its equator and near its poles. So if you imagine a star that kind of looks like this, right? A star with a band around it like that, a band around it like here, a band around it like there. Because that's where it started pulling gas into its poles and its equator. And as the star exploded, all of that was expanded outwards. So these shells, these layers, these rings around the equator and the poles, well, they became stretched out as well. And that's why we get this hourglass shape and these really distinct rings that came from, just before the star was about to explode. So that's pretty cool. So just by looking at a nebula or a supernova, you can kind of tell what happened on the star beforehand. But the Crab Nebula and Hourglass Nebula are kind of really distinct shapes, right? And these are also some certain nebulas in the small Sagittarius cloud. But they are much more circular, right? They're much more circular, which means that they didn't have as chaotic of a supernova as the Hourglass or Crab Nebulas. You can still see kind of just these distinct layers, right? That's like the hydrogen layer. This is maybe the helium layer. This is probably hydrogen. This is maybe helium. And this is a lot more chaotic than here because all these layers are mixed up with each other. But what I'm trying to basically show here is that supernovas have a much more broad and diverse range of patterns because of how chaotic a supernova is compared to a nebula. And at the centers of all these, like right here, and I'm not really sure, but it should be somewhere right there. At the centers of all these supernovas are one of two things. It's either going to be a neutron star or a black hole. So a neutron star is what happens once you overcome electron degeneracy pressure. And as I was saying, if you had those like atoms from before, right, that's your core, and you have your protons and electrons and everything, right? When you overcome the electron degeneracy pressure, that's when your shells begin to overlap with each other, like that. And as they overlap with each other, then the atoms break apart, right? What makes an atom is that it has these shells that do not overlap with other atoms. And once they start to begin to overlap, the atoms break down. And so these atoms just go they go crazy. They no longer become atoms, and they just become particles like this. Just as squished together as close as they possibly can. The idea of an atom is not a thing inside a neutron star. All these particles are just neutrons and protons and electrons all squished together. And that's what we call a soup of neutrons, basically. And because it's so much denser, if you imagine like a white dwarf was this big, a neutron star would be about this big. That's a super big size change that it has to undergo. And as a result, that's why the gravity on neutron stars is sometimes 10 million or 1 quadrillion times stronger than the gravity on Earth. Because that's pretty crazy. And as a result, being so dense and having all these fundamental particles like protons and electrons all souped up together, there are actually a lot of different types of neutron stars. So here it explains that neutron stars are dense cores left behind after a massive star undergoes supernova and explodes. They're only about 10 to 20 miles wide. Can you imagine that? Something like with maybe 1,000,000 times Earth's mass being condensed to something just about 20 miles wide. Right? That's incredibly dense. Like we can't even imagine how dense that is. We only have numbers to try to describe it. So they can have up to 3 times the mass of our sun, making them some of the densest objects in the universe besides black holes. I think this is a really interesting line here where it says, a teaspoon of a neutron star would weigh about 4 billion tons on Earth. A single teaspoon, right? It's literally this much, is 4 billion tons. That's insane. And so here are a few types, the types of neutron stars. So the first type of neutron star is what we call, well, there is, before all these 3 types, there's just a normal neutron star. Normal neutron star, imagine just a star of just super neutrons, none of these other stuff. But there are some special types of neutron stars. And the first type is what we call a magnetar. A magnetar has a super strong magnetic field. And the magnetic field comes from the fact that it has all these fundamental particles moving in a soup inside the star. As a result of that, it creates a really, really strong magnetic field. And that's what these magnetic field lines are trying to show. It's super, super strong. And in fact, it's 100 million times stronger than the magnets that we've ever made. And these types of stars are super, super rare because you don't usually have the conditions to create such strong magnetic fields. And as a result, we've only known about 30 magnetars so far. We've only discovered so many. Another type of neutron star, this one's a lot more common, is what we call a pulsar. A pulsar is roughly, it has 2 beams of radiation that come out from its poles. And the reason for this radiation is because, yet again, its magnetic field. It's not as strong as a magnetar's magnetic field, but it's still strong enough to cause all the radiation inside the star, or most of the radiation, to be funneled towards the poles. If you can imagine the north and south poles right here, and if you imagine like a piece of light, right, a piece of radiation, here are the magnetic fields, right? So it's going this way. If this particle is right here, it would be attracted basically to the north side like that, from within the star. If it was a positive one, then it would be attracted towards this side of the star. And so this is happening all over the star, where things are being attracted to the poles and being excreted out the poles like that. And that's what creates these beams of radiation coming out. And so sometimes what they say that these poles are not precisely aligned with the neutron star's rotation axis. And I'm going to show what that means. And they become what they call a lighthouse in space. I think this is really cool. So let me search up pulsar. Like that. Or let's find something else. Does this work? No, it's not accurate. Here, like this. This one's pretty good as well. Right, you see these, sometimes this is what it means by the rotational axis is not aligned with the poles of the neutron star. And as a result, as the neutron star spins around, its poles sweep across the entire sky, shooting this radiation out into space. So those are pulsars. In fact, sometimes with these, inside this picture, well, this is spinning maybe one time every second or so. So that's still
Is it
pretty.
really fast, like the spinning?
Yeah. So inside these GIFs, the reason why they're spinning so slowly is because, well, we have to be able to see them. But sometimes these, well, they spin so fast, they will become what we call millisecond pulsars, where the fastest millisecond pulsar that we know about actually spins at 700 times a second. 700 times a second. That's really fast, right? But yeah, that's a pulsar. And the last one is, well, you combine the two together. Pretty simple. If you have a really strong magnetic field and you also have the funneling of the radiation to its poles as a magnetar plus a pulsar. So those are neutron stars. And the last thing is that we have are black holes. Black holes are like what happens once you overcome neutron degeneracy pressure. In here, the reason why the neutrons like don't, or all these fundamental particles don't collapse even further is because, like, if you imagine like two balls, right? And if you try to compress the balls even further, well, you can't, because they're solid, right? You can't compress them any further. But if you have so much mass there, what happens is that these balls will merge. Basically, they merge together and they like collapse like that. They get squished together so far. And that's what we call overcoming neutron degeneracy pressure, when even the most fundamental particles in our universe are squished and no longer like those two balls, they're no longer balls anymore. They're just like squished together. That's what we call neutron degeneracy pressure. When you squish something so far that it no longer even exists. As a result, when you have something so dense that it doesn't even exist anymore, then it becomes what we call a singularity, where it's so dense that nothing that we know of, like nothing, like we can't describe a singularity, because a singularity is simply a point in space, where it's so dense that we don't even understand like what it is. It's just you can't describe it using fundamental particles, things like protons, neutrons, electrons, atoms. These aren't things that you can describe a singularity with. It's just a point of infinitesimal density. And that's what we call a singularity. And since that singularity is so dense, if you get too close to the singularity, then the gravity of the singularity will begin to pull you in. And so that's what the event horizon is showing. If you are right here on the singularity, close enough to the singularity, then you're going to get sucked into the singularity. You cannot escape it. And the event horizon is the limit of that. In fact, this gravity of the singularity is so strong that even light, which is the fastest thing in our universe, moving at 300,000 meters per second, still isn't strong enough to leave like the singularity. If a light particle was right here and tried to escape, it couldn't, because it's just not fast enough. It would just fall straight into the singularity. If you were a light particle right here and tried to escape, that's fine. You can escape. And the reason for that being that you're outside the event horizon. You're far enough away from the singularity that you can escape. So the event horizon is that cutoff point, the distance away from the singularity that you have to be in order for you to escape if you were light. That's why the event horizon, everything inside the event horizon is so black, because that's where light can't even escape. So that's why it's so dark. Everything around it you can still see because light can escape, but within the event horizon we don't know what happens because light can't even come out of it. Yeah, there are a lot of really interesting things about the black holes. And I really encourage you to explore that on your own if you're really interested, because we're starting to run out of time today. But what makes black holes so difficult in that to like study is because of their black, right? They don't emit any light. Think about, stars, right? They emit so much light at us, we can just point a telescope at it and we can see it, right? But a black hole, it doesn't emit light. In fact, it sucks it in. So it's really difficult to actually find black holes. In fact, last year was the first time we ever saw a black hole. We actually had an image of a black hole here. This is our image of a
Before
black
that,
hole.
how did we know that there were black holes?
How do we know? Yeah, that's a really good idea, really good question. We thought there were black holes. It's because we know the theory of, we know a lot of physics, right? We know what could happen if you surpass neutron degeneracy pressure, if you become so dense that even neutrons or fundamental particles break down. We can theorize what could happen, but we never had firm proof that they actually existed. Like for example, let's say for example, like Einstein or something, right? He like had a lot of theories, right? And over time, we started to prove them. We had a lot of trust that they were correct, but we didn't have proof. They were just theories. Now, this last year was the first time we actually had firm proof. We had an image of a black hole, and this was that image. And what this shows is, well, you should see the event horizon, right? The event horizon is this dark, this line right here, where, well, that's the event horizon. Inside the event horizon, that's why it's so dark. There's nothing, right? No light is coming out of it. And around it, you see light, right? Because that's beyond the event horizon. You can see that stuff. That's what this is our image of a black hole. It's really blurry. You can't really, it doesn't look like all these images you see on Google, but this is our best idea. This is our actual image of a black hole. You see all this stuff right here, like this isn't a black hole. This is some person drew this. This doesn't even make sense. Why is a black hole like, why is there a plane, right? Why is it like, this doesn't make any sense. This is a bit better, right? This is a really nice image of a black hole or illustration of a black hole, but it still isn't. It is still someone's drawing. Is what someone thought was a black hole. Same thing here. This is what people think black holes look like, but they're not really what they are. So most of the images, like all these images you see here, these are all wrong. These are all illustrations that some person drew. But the only true image of a black hole that we have, the only image that we have is this one. So if you see a black hole that isn't this one, then you know that it's an illustration. Sorry, Braden, how long did you join ago? I didn't see that you were in the waiting room.
I just joined earlier. Wait, no, I just joined now. I was in this class before, but I accidentally left.
Oh, okay, that's my bad. All right. Well, we were just wrapping up on black holes, and we're talking about how this was the only image of a black hole that's really true, and everything else is just an illustration. Yeah, there's a lot of really interesting stuff with black holes, stuff like gravitational lensing, or we have accretion disks, and we call gravitational waves. And there's a lot of really interesting stuff, and what we call Hawking radiation. And there's so much interesting stuff around it because this is where physics breaks down, right? We don't know what happens beyond the event horizon. So that's why there's so much theory and there's so much cool stuff around black holes, but it's so much stuff that I can't really go in depth and we don't have the time for today. but we still have 3 more classes. So what I want to go over the next few classes is stuff like the Big Bang, what we call cosmology, general shapes of the universe. But that might only take up a class or so. So in the future, if we're really interested and we have the time, we can definitely go over some of the interesting theories on black holes and what happens when physics breaks down. All right. So that's will be the end of class for today. We've now covered almost everything on this chart now. On this chart, we still have a few more things left, like binary white dwarfs, types of supernovas, but we've covered almost everything here. Right? We've covered black holes, we've covered neutron stars, pulsars, black dwarfs, white dwarfs, and everything beforehand. Right? So I think we've gotten to a pretty good point in stellar evolution. Right? And now we all have a pretty good understanding about how stars are born and how they evolve and how they die. All right. So yeah, that's the end of today's class. I hope you guys enjoyed.
Thank you.
Yeah. See you guys
Bye.
next time.